Okay class, so today we're going to solve polynomial equations. So some of the theorems, there's 3 theorems here that I want to talk about. So it's a reminder of the rational zeros test. So if you have a polynomial, and this is just the generic of a polynomial, then all possible rational zeros of f can be written as the factors of a0, which you find all the factors of that number, and divided by the factors of an, which is the first number. So for example, if your function f of x is 3x squared plus 9, then you find the factors of your constant term, your a0. So the factors of those would be plus or minus 1, 3, and 9. And then we would divide by the factors of the leading coefficient 3. So it would be plus or minus 1 and 3. And then you just separate into fractions, so you can have 1, 3, or 9 all over 1, or 1/3, 3/3, or 9/3, and that would be the list of all possible rational zeros. So remember, rational numbers are numbers that can be written as fractions, or they have a terminating decimal or a decimal that repeats. This does not give you the list of irrational numbers like square root of 2. So if you had an answer, like if you factored something at 3 plus or minus the square root divided by 4, that's an irrational numbers. This list only gives you the rational numbers. This, of course, doesn't give you the complex roots either. Okay, so this is the list of possible rational zeros, and then we would test them. We would use synthetic division to determine which of those are. And remember, with synthetic division, when we take these numbers and plug it into synthetic division with our polynomial, if we get a remainder of 0, then it confirms that it is in fact a root. So the next theorem says that it's a linear factorization theorem. So if you have a polynomial of degree n, so it's the highest exponent, so my f of x above, it was degree 2, then it has exactly n linear factors. So this was degree 2, which means it would have 2 factors. Think of all the quadratics that we just solved. All quadratics had 2 factors. Sometimes it would be repeated, like x plus 1 times x plus 1, but it would have 2 factors when it's factored all the way. So if something is of degree 4, meaning the largest exponent is 4, then it's going to have 4 factors, and that just says it's written out 4 different factors, where the c's are complex numbers and those are the roots. The last one, it says that complex zeros occur in complex conjugate pairs. So if 3i is a root, then its conjugate minus 3i is a root, and minus 4 minus 2i is a root, then so is minus 4 plus 2i. Remember to find the conjugate, one's minus and one's plus in front of the I. We used that when we were multiplying, or moreover dividing, complex numbers. So these are the 3 things that are important. So let's go ahead and go through some examples. Okay, so the first step to solving any polynomial equation is by setting it equal to 0. So I'm going to add 12 to the other side. Oops, that's minus x squared plus 17x, and then I have a plus 12. So if I apply the rational zeros test, then I take all factors of 12, and I can get my list of possible rational zeros. Okay, so the list of possible rational zeros is plus or minus the factors of 12, which is 1, 2, 3, 6, oops, forgot 4, 1, 2, 3, 4, 6, and 12, all divided by the factors of the leading coefficient, which is 1, so it's plus or minus 1, which tells me the list of possible rational zeros is all of those numbers under 1, or just all of those numbers. So that would be, in fact, my list of possible rational zeros, 1, 2, 3, 4, 6, 12, plus or minus. So that's 12 different possibilities. Of course, none of those may actually be or zeros, because these are just the rational ones. This could have 4 complex roots, or it could have 4 irrational roots. This only gives me the rational. So, but since it is degree 4, we know that it's going to have 4 factors, and hence 4 roots. Okay, so we're just going to solve. So we're going to get 4 answers because it's degree 4. So we're going to solve this without a calculator. So if you don't have a calculator and you need to solve it, you just start going through your your list of possible rational zeros. So always start off with 1 and test if 1 works. So 1 minus 5 minus 1, 17, and 12. So I'm pulling off all of my coefficients in order. I'm not missing any terms. If I was, I would need a 0. Okay, so bring down the 1. 1 times 1 is 1. Add your column. Multiply. Add your column. Multiply. Add your column. Multiply. And you get 24. So it does not equal 0. So this tells me that 1 is not a root. Okay, so what you need to do is try 1. If 1 worked, try it again with the leftovers if you did get a 0, and see if 1 works again. And keep trying 1 until it no longer works. If 1 doesn't work, like in this example, we're going to try minus 1. So let's go ahead and try minus 1. So 1 minus 5 minus 1, 17, and 12. So 1 minus 1, add straight down, multiply, 6, add straight down, minus 5, add straight down, multiply, and in fact we do get a 0, which tells me that minus 1 is a root, and x plus 1 is a factor. Okay, so minus 1 worked, so if it works, try it again. So I'm just going to switch colors. Let's try it again. We're going to try factoring the leftover polynomial. Remember, this polynomial comes from x cubed minus 6x squared plus 5x plus 12, right? Originally it was degree 4, and we got one factor out, so now it's degree 3. So let's bring it down, multiply, bring it down, multiply, bring it down, add, multiply, and we do get a remainder of 0, which tells me minus 1 is a root again, and x plus 1 is a factor again. So now, if I call this polynomial, say g of x, now my g of x, it's x plus 1. From here, minus 1 is a root, x plus 1 is a factor, times we got minus 1 was root again, so x plus 1 is a factor again, and then we have this, which is a quadratic, x squared minus 7x plus 12. Once you get down to a quadratic, you can use whatever quadratic method you prefer. Quadratic formula, factor by foiling, factor box method, or completing the square. But this, it factors simply. Bring down my x plus 1, and then this factors as x minus 4, x plus 3. And remember, this was actually my g of x set equal to 0. So I'm going to take each of the terms and set equals 0. So x plus 1 equals 0, x plus 1 equals 0, x minus 4 equals 0, x plus 3 equals 0. And I get x equals negative 1, 4, and negative 3. And those are the solutions. So if I plugged all of those in to my original equation, I get true statements out. So this is all the zeros of the solution. So it's the zeros of the equation. It's a solution to that equation. And here it is factored completely. These are the zeros, or the roots of my equation. Okay, so remember, list off your possibilities and start trying. Try 1. If it doesn't work, try minus 1. If it works, you get a 0 remainder. Try it again and keep trying it. When you get down to a quadratic, factor it like we did quadratics. Okay, let's move on to the next example. Okay, so for example 2, there's multiple ways I could do it. I could add 16 to both sides and take the 4th root of both sides, or I can go ahead and factor. It's a difference of squares. The square root of this is x squared, the square root of 16 is 4, and make 1 plus and 1 minus. And I have a difference of squares again. So it's x minus 2, x plus 2. Remember, the difference of squares, just take the square root of the first term and the square root of the second term, make 1 plus and 1 minus. When it's x squared plus 4, when it's the sum of two squares, this factor similar to here, except it's with imaginary roots. So it's always going to be x minus 2i and x plus 2i. Okay, because x squared plus 4 can be written as x squared minus a negative 4. And if you think of this as my other term, kind of like where the 4 was, but now I have a minus 4, now it's written as a difference of squares. So it's x minus, what's the square root of negative 4? It's 2i. And then it's x plus the square root of negative 4, 2i. So that's where that comes from. We did that in algebra 2. So now that you have this, you take each term. So this gives you, when you set it equal to 0, x equals 2, x equals negative 2, this gives me x equals positive 2i, and this gives me negative 2i. And you see complex roots come in complex conjugate pairs. Okay, so this can also be written, of course, as x plus or minus 2 and plus or minus 2i. Okay, so those are all the solutions there. So let's move on to the next equation. Okay, so for this one, we want to solve this polynomial. We're giving x squared minus 4 as a factor. Okay, since it's a factor, I'm going to set it up with long division. Minus 4, I had to have the placeholder. 3x to the 4th plus 11x cubed minus 44x minus, oops, I need to put all of them in order. So it's minus 6x squared minus 44x minus 24. Okay, so now I have it in order and I can do my long division. So x squared times 3x squared gives me 3x to the 4th multiplied by the middle term, 0x cubed. 0x cubed multiplied by the last minus 12x squared. Now I'm going to subtract it all, subtract, add now, and I have 11x cubed plus 6x squared. Bring down my next term, minus 44x. I need what goes into 11x cubed, that would be 11x, multiply it out, 11x cubed multiplied by the middle term, 0x squared, then minus 44x. I'm going to subtract, add, goes away. I have 6x squared. This becomes a 0x. Bring down the last term, minus 24. I need 6. X squared times 6 gives me 6x squared. Multiply it. 6x squared. Multiply 6 by the middle term. 6 times minus 4 is minus 24, and subtract, this becomes add, I get a remainder of 0. So this long division just confirms that x squared minus 4 is a factor. I got a remainder of 0. But what it does tell me, okay, so what this does tell me is that my f of x is x squared minus 4, that's a factor. And when I multiply it by that, 3x squared plus 11x plus 6, I'm going to get my f of x equation. And I'm going to solve it, set it equal to 0. So I need to factor this, which is x minus 2, x plus 2. And then I need to factor this last part, this quadratic. You can factor it using the quadratic method or the box method. If I set it up the box method, I need two numbers that add to be 11, and two numbers that multiply to be 3 times 6, which is 18, and those are 9 and 2. So I'm going to have 3x squared, here I have x, I have 9x and 2x, oops. Excuse me, let me back up a bit. So I have 9x and 2x, pull out the GCFs. That would be 2, 3x, x, and a 3. So that tells me it factors as x plus 3 and 3x plus 2. And I'm going to set each of those equal to 0. So I get x equals 2, negative 2, negative 3. And when I set 3x plus 2 equal to 0, subtract 2, 3x is negative 2, or x is negative 2/3. Okay, so those are all the zeros, and the line above it is in factored form. So we factored it completely to a product of linear factors, and then we solved it. Okay, that's all. That is how we solve polynomial equations. Long division, synthetic division. get your equation to factored form, use zero product property, set it equal to 0, and you get all of your roots. So I hope you have a great night.